Hello. So today let's talk about recursion. So you wrote a lot of loop before. You've seen the while loop, you've seen the for loop, but recursion can solve many of the problems you saw before with loops. So recursion basically means you're calling a function. A function is calling itself in order to solve a smaller problem each time. So let's get started with a very simple example. Uh, I want to sum 1 through n. And well, you might have noticed there's better way to do this, but we're trying to teach recursion, so let's get started with that. This is just there's even a formula. You can just plug it in, but wait, let's use recursion. So in order to recurse, we have to have a base case where uh, we want to stop the execution. It's similar to a loop. You want to stop the loop when you reach a certain condition. So for some, our base case is when n is one, that because we know what the sum of 1 to 1 is, it's just gonna be one. Well, so let's just write that down. So I just said it in English, so I'm just gonna write the same thing down. So when we do recursion, it's good to think about the stuff in English first. So the answer is one. Now that aside from a base case, you need a recursive case. And usually it involves a return, well, because we are not using void and calling itself, but we might have to do some other things as well. So let's say if it's not one, it's some arbitrary n. What does this equal to? Well, I know that the sum must include one copy of n. You add n to some other stuff. So what does the sum equal? The sum equal to the sum of the 1 through n minus 1, right? At n. I just said it in English. Now I just write it in code, and you can see this is correct. And another form of recursion I want to talk about is tail recursion. So you might learn that from lecture that it saves space. And I don't have enough time to tell you why it saves space. But I can give you an example about how to make one and and I will explain later what distinguishes these two. So for tail recursion, we need another argument. We have to it's you can see that we're accumulating, so I'm just gonna ask accumulate call it accumulate. Well, you will see later. So the base case, the condition is the same, right? But this time, um this so this is going to accumulate the sum we have so far. So when we get to one, we want to add that to the accumulation result, right? So you can see this is a little different from this time. And now that let's write the recursive case as well. So n minus one, it's the same, but notice that we're not just adding it to the result and returning it. We want to add it to the accumulator. And if I have time, I can trace it out. You always want to call this with zero. You can because you're asking a sum. The sum start with a zero, but what if I say it's the the factorial? Then you probably want to make it start with one. You're multiplying everything together. You cannot multiply everything by zero together. And it's if I do this out one by one, you're gonna see that it's gonna first add n and then n plus one and so on, and you can see this works. So what makes this tail recursive is that notice that it is on the last on every time the function ends, it always calls itself without any additional operations. Well, this you call itself, but you need to add the n to the result, so that's not tail recursive.